All right, Algebra 1 notes. So you're going to copy these down for credit. This is section 3.2, linear functions. All right, so put your name, the date, what period you are in the upper right corner. Pause the video when you need to so that you can copy down what I'm writing, catch up, take a break. So today's about linear functions. So last section we talked about functions, but those are any kind of functions. These are a special group of functions. So what is a linear function? How do we determine if it's a linear function? So I mean, in general, linear functions, they look like very straight lines. They're not curvy or anything. So there's a few different ways that you're going to need to be able to recognize them. One is from a graph. Okay. And the second one is from a table. And the third way is from an equation. So these are three different ways you could be given a linear function or a function that you have to decide if it's linear or not. So you need to be able to recognize it. So a graph's kind of simple. It looks like a straight line. Okay, straight line, could be tilted, it could be flat, but it needs to look like a straight line. Can't have any curve to it. From a table, we're going to do examples of all these. You need to identify if there's a constant rate of change. Constant rate of change. An equation needs to look like this. Y equals mx plus b, where m and b are constants, which means they're going to just have numbers. You're not going to actually see the letters M and B. There's going to be numbers there, but there should be an X. Okay, but we can have, and it's X to the first power. So if you have an X to any other power than 1, then that's not good. So let's look at some examples of each of these situations. So we're going to start with example 1, and we're going to look at graphs. So example 1, part A, we're going to draw a couple examples here. Probably have some problems like this on your assignments this week. Okay, so we're going to make a simple graph. And okay, so this is the graph of our function. Now, does it look like a straight line? Yeah. So we're going to say that it is linear, and we got to give a reason because the graph is a line. Linear is kind of a fancy way of saying line, something that looks like a line. Let's do a second example of a graph. So this one, we're going to kind of draw something that looks like that. Our graph. Now this is a function. It passes the vertical line test that we talked about last time. So it is a function, passes vertical line test. Okay, so that's what we learned before, but it's just because it's a function doesn't mean it's a linear function. It is not a linear function. We would say non-linear because it's not a straight line. So graph, the reason is graph is not a line. So you need to provide a reason for it. You need to show me somehow how that I understand it, that you understand what the issue is. So that's how we recognize it from a graph. Okay, example 2. How do we recognize it from a table? Okay, how do we recognize from a table? So I'm going to give you guys a couple tables. X, Y. There's going to be some numbers in them already. 3, 6, 9, 12, 36, 30, 24, 18. So on these ones, we said it has to have a constant rate of change. So the rate of change is how much it changes from one value to the next. And so we could show that. We say, well, from 3 to 6, we added 3. From 6 to 9, we added 3. From 9 to 12, we added 3. So this is staying the same every time, right? Over here, we're subtracting 6. We're subtracting 6. We're subtracting 6. So these are the same, okay? It could be adding or subtracting. It's got to stay the same every time. So this one is linear. Linear. And the reason is it has a constant. Constant means always the same. Constant rate of change. Rate of change is how much something is changing. Constant means it stays the same. So these all stay the same and these all stay the same. So let's do another one. Another table. And this is how you would show your work. This is how you would show your work, and I would feel confident that you understood what you were saying. So copy down this table. 1, 3, 5, 7, 2, 9, 20, 35. And so let's see the rate change. This is plus 2, this is plus 2, this is plus 2, all good there. This is plus 7, this is plus 11. Oh my gosh, already know it's bad. Plus 15. It's not staying the same. You could do something like this, be like, hey, look, that's the problem. So the answer to this one is non-linear. And it's because it does not have a constant rate of change. So that's how we identify that. That's how we explain it. All right. Third way, example 3 is going to be equations. So instead of a picture, instead of a table, might be given an equation. Now the equations, I already mentioned up there, need to look like, they need to take the form, be able to be written in the form y equals mx plus b, where m and b are going to be numbers, constants, okay? So I'm going to write a few examples here. Y equals 6x plus 1. Does this look like that? Yes, it does. It's linear. Okay. B, x squared minus y equals 0. Is that linear? Well, the biggest thing is the squared right here. Non-linear. It's got to be to the first power. I mean, we could always move stuff around from one side to the other if that was the issue, but that squared is the issue. Okay, C, y equals x. Some people might be like, nope, doesn't have the number x and the number plus a number, but could we rewrite it so it looks like that? I mean, this is saying is 1x, right? So the m value is 1 plus 0. Yeah, that's linear. So maybe it doesn't quite look like it at first, but if you could rewrite it without changing really what it means, and then it looks like it, then we're good. Okay, y equals 3.8. Doesn't really look like y equals mx plus b. It doesn't even have an x. But we could say it has 0 x's plus 3.8, right? Isn't that the same thing as that? And now it looks like the y equals mx plus b. So this is linear. And this is what you could show for your work, to rewrite it to make it look like that if it's not quite like that. Okay? So that's how we do that. Now we're going to talk about a couple different types of domain. We were talking about domain before. So there's something called a discrete domain, and a continuous domain. So what's the difference? I think I probably mentioned it last time we took notes. So discrete domain means you only have whole numbers. So inputs input values, the x values, input values of certain whole numbers. Like if you're buying boxes of cereal at the store, you only can buy one or two or three. You can't buy 1.5 boxes of cereal. You can't cut one in half, right? You can't buy 1 1/3. You can't buy 1.7 boxes. You got to buy whole numbers of them, right? So what it would look like if we were to graph it, for instance, maybe not the boxes of cereal, but just a discrete domain, is you just have these single dots. That's the only values, okay? So the domain of this would be -2, -1, 0, 1, and 2. Like that would be the domain of that. That's how we'd write it. Now, continuous domain is where the input values are in an interval. So that's a whole chunk of answers. So like your age, you could be 15, you could be 15 and a half, you could be 15 3/4, you could be 15.2 years old. Like you're all the ages in between, right? Like you're always like, decimals, fractions of an age. And so in that kind of problem, if we were to draw a picture, now these are going to be a whole chunk of answers. So it might be like -2 solid dot to 3, and then everything in between is shaded because you can have all those values, all those decimals and fractions instead of just the whole numbers. So the domain here, you're going to write as an interval. You're going to say, well, it's everything between -2 and 3. So it's greater than or equal to 2, and it's less than or equal to 3. That's how you would write the domain for a continuous domain. Okay? So that's discrete domain and continuous domain. So certain problems, it makes sense to have discrete values, only certain whole numbers, and some you can have all the values in between. Now I'm going to do a word problem, and we're going to have 2 word problems, but one we'll do together, and then the other one I'm going to have you look in your textbook and copy it down as part of your notes to get credit. So let's look at example 4. So this is like an application problem. And so the problem says, the linear function y equals 15x represents the cost y of concert tickets. Each person can buy a maximum of 4 tickets. Okay? A, find the domain. Is it discrete or continuous? We were just talking about that. Is it discrete or continuous? And then part B, you're going to graph using the domain. Okay? So, what's the domain? Well, the domain, like how many tickets can you buy? What's the input? So A, the domain is you can buy 0, 1, 2, 3, or 4 tickets. You can buy 0 tickets, right? So that's your domain. Is it discrete or continuous? It's discrete. You can't have parts of tickets, right? So because it only has discrete, since the domain only has whole numbers. Okay. Now, to graph it, we're going to make a table. So we're going to put x, we're going to put y, we're going to put all the domain 0, 1, 2, 3, 4. So usually the domain, those are the x values. And then y equals 15x. So y equals 15x. It's a linear function. It does look like a linear function, right? It's y equals 15x plus 0. It looks like y equals mx plus b. So that's good. Maximum 4 tickets. You buy 3, 2, 1, 0. You can't buy negative tickets. You can't owe any tickets. So if I plug 0 in here, 15 times 0 is 0. If I buy 0 tickets, my cost is 0. If I buy 1 ticket, my cost is 15. If I buy 2 tickets, my cost is 30. If I buy 3 tickets, my cost is 45. If I buy 4 tickets, my cost is 60. So now we can use that to graph. Let's create a graph. And we'll put 1, 2, 3, 4. Tickets are the x-axis. And then we could say, like, 10, 20, 30, 40, 50, 60, 70. So we can go up by tens just because they're going to be really big numbers. I don't want to have it take the whole graph. So 0, 0, you plug in 0, you get 0 out for y. If you plug in 1, you get 15 out, right? How can we do 10, 20? If you plug 2 in, you get 30, right? I'm just drawing those to help line it up. If you plug 3 in, you get 45. If you plug 4 in, your cost is 60. Now these are nice solid dots. We cannot connect them because that would be a continuous graph. You can't buy anything in between, right? So you can't connect them. You got to leave them the way they are. This is the cost, by the way, in dollars. So we can't connect them. Now, what I want you guys to do for the rest of your notes, so this is going to be part of your notes to get credit for your notes. Example 5 is a continuous example application, and I'm going to have you just look in the book, and it's called Graphing Continuous Data, and it's on page 115. So I want you to copy down example 5 on page 115 for the rest of your notes. After that, you need to upload your notes to Google Classroom to get full credit. You need to have all the notes. Everything I wrote needs to be on there. Everything. Okay? After that, you're going to do monitoring progress out of your book. Page 113. Starting on page 113, 1 to 12 all. They're all on the bottoms of the pages throughout the book. They have little blue arrows that you can play that will show exactly how to do each problem, so there's no excuse to get them wrong. You're not going to be submitting them through Big Ideas. It's not set up that way, but you will upload all the problems with all the work and all the answers boxed fully, all of them, and get credit. Upload them to Google Classroom. Okay? That's it for today. I hope you understand what a linear function is now.